Well, let's welcome back Lorenzo for his second lecture.
Thank you. So yes, thank you. Let's go back to my picture here. So I changed the name of the solution map to lambda since phi was already used for something else. Now again, in order to motivate this for people who did not choose to to do this in their life. So again, you are studying, for instance, the dynamical 543 model. Okay, so maybe you are interested in the invariant measure. Okay, but I told you that the dynamics is constructed in order to at least approximate the invariant measure for large T. Okay, so you are anyway close to your static 543 model. And now this theory gives you a random variable which has, okay, so almost for large T, this law. Okay, so this should already be something that looks useful. So you have a concrete construction which is based on, as I told you, two operations. So one which is probabilistic. You start from a space-time white noise or a regularization, and you construct some explicit object. So I insist on this. It is really something that you control by hand. I will show you.
Will you translate it into language of the previous speaker?
Of Felix?
Felix, yeah.
Yes, so I will, yes.
So could you translate it?
Yes. Can you wait a few slides? Yes, I will do this. So you start from the noise and you construct an explicit object. Okay, and then there is a more, say, mysterious, maybe so less explicit map, but which has very good properties. It is continuous in a certain topology, etc. Okay. So this is one advantage. So the second advantage for me is that so the renormalization operation, which I will also try to describe, here is done at the level again of a random variable. So again, also x epsilon is a random variable. X hat epsilon is another random variable, and there is an explicit again group action which goes from x epsilon to x hat epsilon. Okay, so you don't study correlation functions or say expectations, okay, which are renormalized. You study directly a random object, okay, which seems to me more say easier to visualize. Then, as I said yesterday, the precise correspondence between the two pictures is to me still somewhat unclear, okay, but I'm pretty sure that one can make a bridge between these two words, and I hope this will be done maybe during this semester, or anyway the seats can be okay already done here in this during this semester. Okay, then there was a very interesting, very legitimate question yesterday about this object. So lambda of x, okay, lambda of x epsilon is u epsilon, which is by definition the solution to this regularized equation, but without renormalization. Okay, while so u hat epsilon is by definition lambda of x hat epsilon. So there is no reason a priori that u hat epsilon satisfies any equation in some sense. So anyway, it is not contained in the definition. So it turns out that okay, indeed u hat epsilon in general satisfies an equation, and in particular, so if you choose well your x hat epsilon, it will have exactly this, the equation will have exactly this form. So lambda again is the same, lambda does not depend on epsilon. So I confirm and stress again that x hat epsilon does not know in advance u hat epsilon. Okay, so this is just a modification of x epsilon via some constant. Okay, so it's again an explicit object, which seems again a very convenient situation. Okay, again, I hope that we'll manage to see the computations in phi for 3. Okay, this more or less I explained. So yeah, so I want to go ahead. We start with phi for 3. Okay, so it will be a little bit disconcerting at first, but you have to be patient. It is not very difficult after all. So you will accept a certain number of objects, at least of definitions, okay, and then you will be rewarded at the end of your patience. So we fix a family of symbols, okay, which are relevant for phi for 3. So the symbols depend on the equation that you consider. For KPZ, they would be different. Okay, but we want to study phi for 3. So they are, apart from xi, okay, which would be just one dot, and apart from xi, which represents classical monomials. So you have a few trees. Okay, you see this has 3 dots and 3 edges. These 2. This has how many? 5 edge dots and the structure, etc. Okay. Now these trees represent so combinations of products, which are the branching points, and kind of integrations or convolutions. So we'll see more precisely later when you have edges. So leaves represent the noise, and these x's just represent okay, classical monomials. Now this is similar to Feynman integrals, although for the moment there are only 3, so later we will see also loops, but not today. So okay, another difference is that here these are going to represent random variables. Okay, so typically Feynman integrals are results of integration, so they are real numbers. But here these will contain the noise, and so in the end you will have a rather random variable. Okay, in fact Felix has introduced the more symbolic notation, so the I looked slightly different, but this is a problem of LaTeX. So you can represent, you see, the dot, the leaf as a xi, and the edge as a I. I stands for integration, and then this when you branch, this is interpreted as a product. So this is equal to I of xi cube. So the whole of I of xi cube, and also this, you see, you take I of xi cube, then you integrate. There is an additional edge, and then you multiply by I of xi, etc. So you can represent all of these symbols in this notation. Sometimes it can be more convenient. Yeah, so again, yeah, okay, this is not completely precise. Anyway, essentially the symbol I represents a convolution with the green kernel or some okay, variation, and so there is a commutative product of these trees, which is given by the identification of the roots. Yes, this is true. At the same time, you do not want to multiply any pair of trees, okay, because this will not make necessarily sense in the end. So for instance, you want to accept, so okay, don't forget that the theory is meant to work on distributions, okay? So for instance, this, so the first example will be a distribution. So you will manage to give a sense to the product, so the square of it, to the third power of it, but then you stop there. So you don't try to. You could fail to give a sense to higher powers, and therefore it's not really a complete product. You just take some products. So these products you consider, this product you consider, but not any possible product. Okay. Okay, which is again the reason why I restrict my family to relevant objects, not all possible objects. Now, Felix has defined so homogeneities, and so this is done exactly in the same way here. The noise has the same homogeneity as in his first example. So this is for 543 because you have 3 space dimensions which count -1/2, one time the dimension which count -1, and so this is the result, minus some small kappa which is fixed once for all. So these are the classical rules for standard monomials. Okay, I forgot to say what happens for the product. Is it somewhere? No, I forgot to write it. Sorry about that. So when you integrate, you add 2. This is again related to the fact that by the Schauder estimates, the green function is supposed to improve well, regularity by 2, although homogeneity is not really about the regularity, but so this is the correct. And then when you multiply, the homogeneities are additive. So this is so the tau 1, tau 2. Okay, so the homogeneity is additive on the products, which is okay. Very. So again, if you think of a classical monomial, so the degree of the kth power of x is k. Okay, so which is k times. So you really want to mimic these properties. Okay, so I've written here the homogeneities of all the relevant terms, just as an exercise. So, okay, psi is here. So this one is, you apply this rule. It's the homogeneity of psi plus 2. So this is the result. This is twice the homogeneity of this, which is that. This is 3 times the homogeneity of that, which is this. Okay, this is you have 5 times this branch with a leaf, and then you have an additional edge here. So this is minus 5 over 2 minus 5 kappa plus 2, and this is the result. These two have the same homogeneity, which is minus 4 kappa. This is this one plus 1, okay, so it's minus 2k, and these two are so this one plus 2, and so it's 1/2 minus 3 kappa. Okay, so this is these two are positive, and the rest are negative. So okay, with respect to the classical theory of monomials, so you want to introduce negative degrees, negative homogeneities, okay, because you want to have distributions. Okay. Okay, then I define, but later we will not mention this anymore, the parabolic distance. So you are in a 4-dimensional space, but the first variable is time. It plays a different role, so there is this distance that I will use without further mention later. It does not really, okay, just because otherwise certain formula may be wrong, but morally it is a standard distance.
But
Yes.
is it really a metric? I mean,
Yeah,
1/2.
it is. It is a metric. It's not a norm.
It's not a norm.
It's a metric. Okay. So it would not be a distance if you put a 2, but 1/2 works. Okay. Now, the canonical model. So this would be what is. Sorry, I go back. What you do here, you go from psi epsilon to x epsilon. So I want to build this first choice that you make, which seems natural and canonical, and then you will have to modify it later. So, and this is exactly what also Felix has introduced, but I do it in this example. It's again, everything is completely explicit, although okay, we will maybe a bit disconcerting again, at least at first. So everything depends on epsilon because I have psi epsilon. Where is it? I forgot also psi. No, it's here. So pi epsilon x. So you remember there are two variables. Also, Felix insisted on this. There is the base point, which is x, and y, which is the generic variable. Okay, so maybe I start from the classical object, which is this one. So I write a monomial centered at x with now a generic variable y. Okay, so this you accept. It's y minus x, so the ith component. So x and x and y are these 4-dimensional variables. They are space-time points from now on. Okay, you multiply monomials in the standard way. So on the noise you have this definition. So in fact you decided that psi is given by this. There is no so the base point does not play a role. Okay, and then you have to accept this term. Now, what do you do when you integrate with respect to, so with I? So your first guess would be this recursive definition, so that you take convolution of G with so the monomial of the 3 tau, and then you base that x computed at y. But then, okay, this may not be a monomial anymore, in the sense that it may not be small when you want it to be small. So when y is close to x and the homogeneity of the tree is positive, so you want this to be small, and then okay, you are forced to subtract this quantity. So it's the same thing but computed for y equal to x. Okay, so this will be enough. So okay, in general, in KPZ, for instance, you may go further with a longer Taylor expansion. For instance, so this is the Taylor expansion at order 0. You may have order 1, order 2, etc. In general. But so here for 3, we stop at order 0. It will be enough for the trees that I want to use. But okay, as I told you, Taylor expansions play an ubiquitous role in this theory, and this is one point where they appear. So in order to have a monomial, a generalized monomial, this needs to be small when y is close to x, and when the homogeneity is positive, and therefore you define this Although it seems complicated, but it is quite natural. Yes.
So, I mean, that was exactly in my course, kind of these red terms,
Yeah.
which one had to, which I insisted on that they had to be there for the same reason. And
Exactly.
it was a specific case of what's done here in the general setting.
Yeah, absolutely. Okay, so let's check explicitly a few terms. So this I said is given. Okay, this, remember that in fact the only positive trees are this one. So all these trees are negative at first, so there is no recentering. You just apply this rule, there's no, and then the multiplication rule. So this is the square, this is the cube, this. Okay, here you use the multiplication, so this is negative, so you do not recenter it. So by the way, there is no integration, so this is just a product of this times this, but this one has this term, and then this one has this quantity. This one is positive, and so you have to subtract the value of x. Okay, it's boring, but I have written also the next four trees. So this is negative. Let's check. It is what is it? Did I forget it? It's here, right? No. No, because it has two. I forgot it. Maybe in the list. Okay, it's here, but I forgot to maybe to compute the homogeneity. It's the last. And then it's positive. Okay, it's positive. Good. It's one of the positive ones. So yes, okay, it's positive, but it is not the integration of something. It is first a product. Okay, so first you apply the product rule. So this term gives this one. Then, okay, here there is a small inconsistency in what I'm telling you. So the other tree without this branch is not in the list. Okay, because it's not really relevant for what I do. But I just compute. I apply the same rule and I compute this object. So the other tree is positive. If you check. So it is -1 plus 2, so it's like +1 minus 2 kappa. Okay, if it were in the list, that would be okay. And then it is okay. It is this, and the same works for the next trees. Okay, you see they look very similar. This is a square because here you have two branches. This is a square because below you have two branches. Here you have 3 branches here, and then you have a cube. Here you have 3 branches and then 2 branches, so you have a square and a cube. Okay, so it's completely automatic. Okay, so and here everything is well defined because psi epsilon is smooth, so there is no problem. Okay, can I go on?
So
Yes.
sometimes, would you ever have a situation where you have to make a subtraction on both? You have a subtraction
Yeah.
there on one, but you might have to make subtractions on both.
Yeah. For instance, if you multiply by x, or if you multiply two positive, suppose you take two copies of this and you multiply them, then you have this. Yeah, but this will not be relevant in our list. Okay. Okay. So the idea again is that these are new monomials that you want to use to approximate locally your solution. Okay, so if you add these monomials to your tools, then as Martin wrote in his paper, the solutions will look smooth. Okay, on the if you compare the solution to this, so these objects will be rough, but once you incorporate them in your tools, the solution will, in comparison, will be smooth. Okay, it will be like a small perturbation of this object. Okay, you also have to build the gamma, so gamma epsilon. Now, also here you have a kind of recursive construction. So this acts, now remember that this is an operator which acts on now the linear span of this family of trees. Okay, these are the definitions that also Felix has given. On the noise, it's trivial. So on this, it is also trivial. On products, it is multiplicative. For example, okay, because of these two properties, you have immediately this fact. Okay, but further, so you can use a formula which Yvan Brunet has found, which is recursive. Now the computations are okay, not impossible, but not extremely amusing either. So, for instance, now we can try to do this. So this tree is a product. So this you use the product rule. So you know what happens for this lower branch. It's a tree, so it's left invariant. Now the big tree is positive. So again, you have this additional term, which turns out to give this quantity. Okay, so there is not much one can say. That these objects have their expressions, and they do what they have to do. So notice, for instance, that this has the nilpotency properties that Felix has stressed. So I'm not repeating them, but okay, this is positive. So the gamma acts on this as so itself, so identity, plus in this case one term of lower order. So this is positive and this is negative, so they are certainly in the good order. And this is okay. This is a function which depends on y and x. It's again explicit. So yeah, and same for this. Blah blah blah. Okay, you can compute all these terms. In itself, this is not very instructive, but at least you see what they look like. Okay.
Can I ask somehow for this? Can you do one of those computations? Because
okay,
somehow you are saying you are doing something with full tree, and write it as multiplication. So which one? How you somehow do multiplication first, and then somehow think about
okay.
homogeneity of full tree, or
So you want to do? Okay, we can try. So you want to do gamma xy of this. Okay. So this is gamma xy of, say, in this notation, I of this product, and then you are in this setting. Okay, so this is equal to, so I of gamma xy of the product minus, so the homogeneity is positive, so you do have this term. So this is pi x of what? I of gamma, so xy of this. So this all computed at y. Yes, times 1 times 1. Okay, so what is this? We said that on this tree, this gamma xy is trivial. So I mean, it's identity. So I do this, I do this. So I get back my initial tree minus, so pi x of my initial tree, which I compute. No, yes, I did not. It was this part. Okay, without this product. Okay, and then so it is this blah 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 function times 1, and then when I go back, so I had this additional branch which I have to multiply back, so it's here, and then it multiplies 1, and it's here. Okay, it's yeah, it's this. So why okay, why do I do this? So because a relatively simple algebraic result is that you have this compatibility condition, again, that Felix defined. Pi x of gamma xy is equal to pi y. And so the gamma the gamma operators work in this way. So if you compose them, xy compose yz, it's gamma of xz, gamma xx is identity. Okay, so this is the algebraic part of the definition of a model. So the first relation is what makes the space of models, or at least, yes, this, yeah, no, all models have to satisfy this, so is what makes space of models nonlinear. Okay, so if you only use the pi, the pi x, you can think that everything is linear, okay, because you can sum pi x, but the gammas have to be attached to the pi. So if you sum the gammas and the pi, so you will break this rule in general. So yes.
Can you say again how you knew that gamma xy of this little tree was the tree itself?
Because of this. Because I said that it was the identity on this tree, and so I was already, if you want here, I was already applying this rule. So this term is 0 because the homogeneity is not positive. Gamma is trivial on psi, so I get this, and then I apply the multiplication rule and I get this, and so on. Okay. Okay. So for the algebraic part, you can amuse yourself. It's very clean. But so it is very important to have also the analytical estimates. Okay. So this is less my responsibility than it is for Felix, but it is crucial, okay, that you do not get too excited with algebra and you forget the analytical part, because otherwise it simply doesn't work, doesn't give anything. Okay, and so I just remind you that so you need okay, these are just the weak or the weak. No, sorry, no. The correct formulation is what Felix does with this risque test functions, but at least formally. So these are the requirements. So pi x tau of y has to be bounded locally by x minus y to the homogeneity of tau, and if you sigma star now in my notation is how do you say, like the functional which gives value 1 to sigma and value 0 to the other trees, okay, and then it's extended linearly. So you want that at level sigma, gamma xy of tau behaves like x minus y to the tau minus sigma for all sigma less than tau. Okay, so and again, so this is very natural because if you compare with the standard monomials that I was mentioning here, this is equal to this, so it's certainly bounded by x minus y to the kappa. Okay, and so for the gamma you have this binomial expression, and so if you check this, so here homogeneity of sigma would be I, homogeneity of tau would be k, and then so the coefficient which multiplies x to the I is this one, and it is certainly bounded by x minus y to the k minus I, so in absolute value. Okay, so again you are extending to a more complicated setting expressions which are very simple for monomials, although maybe you have never seen them like this, and that's why it is a bit disconcerting. Okay, now in our canonical but so non-classical. So I'm adding monomials, and I'm using this canonical construction. By the way, I didn't stress this. What is canonical here? By canonical, I mean that I am considering the canonical multiplication here, which is exactly what creates problems then for renormalization. This is exactly what I will have to modify later. Okay, the rest will the rest will look very similar, but this will be dropped. Okay, but for the moment we are still there. Now the analytical estimates are trivially true because for the moment everything is smooth. So they are really significant only if they are uniform in epsilons. Only when you remove the regularization they should remain true, which however will not be true in this context. So we will have first to renormalize. Okay. Okay. Again, so just to continue on this analogy with the classical setting. So again, sorry, I'm repeating what Felix already wrote this morning. But okay, repetita iuant, they say in Rome. You have a function which is classical, Hölder, okay, C gamma, function is f. Now you collect its derivatives in this expression, okay, and then it is easy to check that u of x minus gamma xy of u of y can be written like this, okay. Okay, it's just an easy computation. And then you see that the coefficient which multiplies x to the k is a Taylor remainder. So this is the kth derivative of f. So it's the Taylor remainder of the kth derivative at x, where I am expanding around y. So it's the opposite respect to what we did for pi x. Now we are expanding around y, and the variable is x. And so this is by Taylor theorem of order x minus y to the gamma minus k.
Should this be I greater than or equal to k in the sum? It looks a little strange because I would have thought you wanted that to be the Taylor expansion of f of k.
Yeah, no, I'm sorry. Yeah, no. I made a mess here. So this should be, sorry, you're right. So this should be the sum. Okay, let me write this again. Okay, that should be fk of x. So now I'm Taylor expanding this, so I should add the derivatives. So indeed, this should be y less than gamma minus k of x minus y to the I over I factorial k plus I at y. Okay, maybe this makes this is more correct. Probably yes. Sorry, I made a mess with. So this is the Taylor expansion of fk up to order gamma minus k. So this is okay, yeah. And then it is of order by x minus y to the gamma minus k by Taylor's theorem. And again, this is exactly the definition of the D gamma space that that Felix gave 1 hour ago. And so the reconstruction theorem here is just trivial because you define so a function. It should be a distribution in general, but here it's just a function by computing the pi y of u at y. Let's explain. You see u of x, u of y is a sum of symbols, so you can apply the pi y to it. So this becomes a function of some variable, and then this variable is here, it's set to be equal to y. Okay, so in fact, in this case, all terms but the first, so the zero term, so all terms but the 0, 1 disappear, and you just remain with phi f of y. And then what the reconstruction theorem says is just that, again, you have the Taylor expansion of f at order gamma. Okay, I'm sorry. Maybe this is just confusing you, but this is absolutely classical. It's just a different way of writing classical formula. And it is a way which is now ready for the non-classical setting, which is this one. Okay, so again, it's the definition that Felix has shown you. The space of d gamma. Now I fix gamma equal to 1 plus kappa because this is what is again relevant for 543. So the space of functions d gamma, which is like the space of Hölder function, this generalized setting, is given by this definition, okay, this requirement, which is exactly what the generalization of this. Now, a very important remark is that the space d gamma depends on the model. So in particular, if the model depends on epsilon, then the space also depends on epsilon, okay? So you really have to be conscious of this.
Do you allow that? You want
Yeah.
to do that?
Yes, because I mean, your monomials change with epsilon, and then also the functions that you want to, you can approximate change with epsilon, okay? But there will be a stability with respect to this operation. In a sense, at least the solution to the PDE will be stable in epsilon. Yeah, and then again, so in this generalized but still smooth setting, the reconstruction theorem is just based on this, on computing the pi x of u at x, and then so again, what in this slightly sloppy way, the reconstruction theorem says that so this is a global object, so a function or a distribution. So if you fix any x, which is a base point, so around x, this function has this expression as a Taylor expansion. At order gamma. Okay, so you start from an object u, which is somewhat formal. So you're not. So okay, so you decide. Yeah. So it is not clear that such object exists. So you decide at each point a bunch of coefficients. And then the problem is there really a global function or distribution which has these coefficients at each point? Okay. Okay. The reconstruction theorem says that this is the case if you have this compatibility. Okay. It's a very you can forget SPDs. So it's a very beautiful idea, so which may be used in really other contexts. So of yeah, so giving local specifications in every point in this rough, okay, generalized setting, and then finding an object which is well described locally by this local specifications up to some order.
Does it make any sense at this stage in your original picture, this x hat? You had this x.
This is still x. Okay. Okay. Good. I am still at the level of x. There is no hat. What I'm doing is preparing the stage for the construction of this lambda. Okay. So this lambda will be constructed as solution of a certain fixed point in a Banach space. D gamma is the Banach space. Okay. Yeah. So again, yes. So it's a PDE needs a kind of function space where it is okay, embedded, and now I still have 2 slides, I think. I have 2 examples of such D gamma functions. Now there is one example which is very, very simple. So you take any tree in your list of trees, or any linear combination thereof, and then you define u of x as gamma xz of tau for some fixed x. So if you go back to the computations, you can take this, you fix a y, and you can take this as a function of x, so it's relatively simple. Okay, but it may be much more complicated for bigger trees. So anyway, it's a completely general result that the u of x minus gamma xy of uy is this times this, but this is equal to gamma xz, and then it's 0. So this function is not only Hölder, it's analytical, if you want. It's a polynomial. It's a generalized polynomial. So again, it's rough, but compared to the tools you have added, it's very smooth. This is the right way to look at it. Okay. Good. So the next example is slightly more sophisticated. So I have chosen these 2 trees, and I have multiplied them by a of x and b of x. Okay, I make computations. I apply the formulae of the previous slides, and so please trust me. You get these 2 expressions. Okay, so the 2 trees are multiplied by these 2 expressions. So let's see. The definition is that, so at you remember at level sigma, this must be bounded by x minus y to the gamma minus sigma. So I have decided that gamma is 1 plus kappa. So if sigma is the second tree, what is it? No, yes, the second tree, then its homogeneity is this one. So its coefficient here, it's b of x minus b of y. This must be bounded by x minus 1 to the gamma minus sigma is 1/2 plus 4 kappa. So b has to be Hölder with this parameter. Okay. Now the other requirement is more interesting because you get this. By the way, so the power is 3/2 plus 2 kappa. And now what is this saying? This is saying that so a of x minus a of y minus, so b of y times this expression has to be smaller than that. You see, this is itself somewhat small when y is close to x. Okay, in particular here because everything is smooth, but again we expect this to be uniform in epsilon when epsilon goes to 0. And so this looks again like a Taylor expansion of the function a, okay? This is centered at y, and then this is a kind of a new monomial, okay? Again, it's centered at y, and the generic variable is x. So a is, okay, in Massimiliano's terminology, so a is controlled by this monomial, and the derivative of a with respect to this monomial is b. Okay, so if in a classical setting, you would see an expression like, well, actually we wrote it before. So at order 1, right? So expression like this becomes, so f of x minus f of y minus f prime of y times x minus y, okay, are bounded by something. So here you are replacing this by something more complicated. This becomes b, and this becomes a minus a. Okay, so this is really controlled paths in Massimiliano-Gubinelli's definition, but transferred to this setting of regularity structure. So again, so you see that the whole structure is extremely coherent, and so you see these objects appearing all over the way. So I don't know, do you have any questions? I think this is very express, and again, so this allows me to advertise once more the use of algebra here. So this looks nice, but if you try to write explicitly all the expressions which can appear in in such a definition, so they can take 2-3 slides, so it's huge. So you need really a language which expresses compactly all this. Yes, there was a question?
So if A doesn't have enough regularity, then that writing says, okay, it's like a control path. But then if A has smooth regularity, then you know that's okay. You introduce something, then difference has only the 3/2 Hilbert. Then it doesn't say. I mean, right? I mean, your analogy to the control path is only when A is rough. And what does it say when A is smooth?
No, I'm saying that, for instance, if you replace this by Brownian motion, okay, b of x minus b of y, this is exactly the definition of a controlled.
A is rough, because if A is smooth, I mean, you are inserting something which is.
No, I don't want necessarily A to be smooth.
In this case, you might get a huge improvement in the value of the constant, right?
Okay.
It might be smooth, but with a derivative that's very big, but this constant might stay fine.
Okay, time is also almost finished. So the next step will be now to go back to the equation. So why do we want to do this? So we want to consider the solution to the regularized equation and find a u, which is its Taylor expansion in this generalized setting. So in particular, such that the reconstruction of u is the solution. Okay, so we'll see tomorrow that u has to be of this form. So you see there are a few of the relevant objects which appear. Okay, so this is the kind of generalized Taylor expansion of the solution in this setting. Okay. Okay. Then again, the point will be, so this does not converge as it is. It needs to be renormalized, and we'll see that the functional expression of u does not change. So this is a very nice fact. But then, okay, when you reconstruct, you get the famous C epsilon, U epsilon that you need. Okay, so again, if I go back to my picture, I have what have I done? So I have constructed this object. Okay, and then the next step is to construct this one and show that the result is this renormalized equation. Okay, and then I will maybe, if I have time, try to explain why this has some chance to converge, but that's okay. Another quite difficult story. Okay, I stop here. Thanks.